Today's lesson is biconditional statements, and I'm going to go ahead and explain to you how do you write a biconditional statements. Remember that in our first lesson we talked about if and then statements. Those are called conditionals, or we say P implies Q. Now the converse is Q implies P. Now what happens if the conditional and the converse both are true? If both are true, then we can write a biconditional statement. So let me give you an example. An angle is a straight angle if, so that's a hypothesis. The conclusion is only if its measure is 180. So that means if the angle measure is 180, then the angle is a straight angle, and that's true. We know that if an angle is a straight angle, then the measure is 180, so that's true. So that's why we have that if and only if. That means it's true in both directions. So I'm going to write true in both directions. In other words, the conditional and the converse are both true. So let me write the following statement. A biconditional statement is a combination of a conditional statement and its inverse. And that's what I was telling you first. A biconditional contains the words if and only if. So if I write the following biconditional, it says consider the true conditional statement. So I'm already telling you that it's a true conditional statement. Write the converse. Okay. If x equals 5, then x plus 15 equals 20. So that's true. Now I'm going to write the converse. If x plus 15 equals 20, then x equals 5. So the converse is also true. So both are true. So now we can write the biconditional. And it says when you subtract 50 from both sides to solve the equation, you get x equals 5. Because both the conditional and its converse are true, you can combine them in a biconditional using the phrase if and only if. So if and only if combines the two phrases to make a biconditional. If x equals 5, if and only if x plus 15. So that's saying that you can go in both directions, okay? And that is a biconditional. In geometry, it's important that we be able to write good definitions. And here would be an example of a definition. An apple is a fruit that contains seeds. The statement is true as a description of an apple. Exchange an apple and a fruit that contains seeds. The converse reads, a fruit that contains seeds is an apple. A fruit that contains seeds. There are many fruits that contain seeds but are not apples, such as lemon and peaches. These are counter examples. So the converse statement is false. So remember the initial statement, an apple is a fruit that contains seeds. So if I change both statements, that would give me the converse, and that isn't a good definition because there's some counter examples that make this false. So the original statement is not a good definition because the statement is not reversible. In other words, if we write the converse is false. So this is not a good definition. So we want to make sure that we practice writing a good definition in geometry. So we're going to go ahead and do a quick check. Consider the following true conditional statement. Write its converse. If the converse is also true, combine the statements as a biconditional. Conditional. If 3 points are collinear, remember what the word collinear means? Then they lie on the same line. So this is your hypothesis. This is your hypothesis, and this is your conclusion. In other words, I'm going to write hypothesis, and this is your conclusion. P implies Q. So what we're going to do now is we're going to switch. If 3 points lie on the same line, then they are collinear. So you notice we have Q implies P, and we know that this is true, and we know that this is true. So both statements are true. So the converse is true. So how do you write a biconditional? 3 points are collinear. So we write 3 points are collinear, and then you notice we write the if and only if. We write the if and the only if. They lie on the same line. So that's how you write a biconditional. Okay, we're going to check if this is a good definition. So let's go ahead and do this quick check. Is the following statement a good definition? Explain. A square is a figure with 4 right angles. So we notice that this is your P and this is your Q. And we know that a square is a figure with 4 right angles, so that's true. What happens if we switch the Q and the P? We're going to get the converse, aren't we? So that's going to be the converse. Remember, Q is going to be the conclusion, and P is going to be the hypothesis. We just switched it. That's going to be the converse. It's not a good definition because if we switch it, it would say if a figure has 4 right angles, if has 4 right angles, then it's a square. That isn't a good statement because we can say as a counterexample, a rectangle has 4 right angles. So this would not be a good statement because it's not true when you write the converse. So this would not be a good definition. It says if a figure has 4 right angles, then it's a square. But like we said, we can have a counterexample. A rectangle has 4 angles, so this would not be a good definition. Okay.